Okay, so moving on, now that we've seen an overview of generative machine learning and the connection of generative machine learning to nonlinear mixed effects modeling, uh, maybe we can take a step back a little bit and discuss deep learning models and in particular neural networks and how to train them. And understanding at least some of the fundamentals of deep learning is going to be quite helpful, especially when we try to combine these neural networks with more mechanistic models and build these scientific machine learning models that utilize the flexibility of neural networks, but also sort of the knowledge embedded in some of these mechanistic and scientific models that we developed over the years. So in this part of the training, we'll basically be going through some of the fundamental concepts of what a neural network is. In particular, we'll be focusing on the multi-layer perceptron and also how to train it, what are the different parameters that the neural network has, and concepts like regularization and overfitting and so on. So let's get started. So a neural network there are basically many architectures of neural network or neural networks, and each architecture can serve a slightly different purpose and have slightly different sort of connections between the inputs and the outputs. But fundamentally, a neural network is just a function, essentially. And a function generally will have some inputs and some outputs, and that's exactly what this function here is. So this here is like a nice sort of schematic of a very simple multi-layer perceptron. In fact, it's a single layer perceptron. There's only one or single hidden layer, rather, in this case, perceptron. And in this case, we have three layers, basically. So there's the input layer, here, and then there is one hidden layer, and then there's an output layer. And so a neural network is generally going to be made by stacking these layers on top of one another, where the input comes in first in the first layer, and then it gets processed somehow. We'll see how this processing happens, and then it becomes sort of, or it gets output to the hidden layer, or becomes the hidden layer, and then the hidden layer values get again processed in some other way, and then that becomes the output. And that's sort of usually the flow of the data, basically going from the input to the output in any kind of deep learning model. Now, some deep learning models will have different types of layers, and generally when you have layers, there are sort of basically every input goes to every output. So let's sort of break this down first. So each arrow here with a coefficient on top of it, or some parameter that's basically like W11 or W12, etc. This implies that we will take this input here, which is x1, and then we will multiply x1 by its corresponding coefficient, which is this W11, and then we will do the same thing for x2, multiply it by its corresponding coefficient, and this is the arrow that's going into this sigma here. And then we always assume that there is an input 1 basically coming in, which is a constant, and that's sometimes called the bias term. And so 1 here also gets multiplied by a weight. So this weight gets a special name. We call it the bias rather than, so all these coefficients here are usually called the weights, and the coefficients of 1 are called the bias. It's similar to the idea of an intercept in a linear regression model. And so the 1 here gets again multiplied by some coefficient, and then the output of 1 times b1, x2 times w21, and x1 times w11, all of them come together here, and then we sum them up together. We just add them to each other, and then we apply something called an activation function. Now, an activation function is just some nonlinear function. It could be like a tan h or hyperbolic tan function. It could be a sigmoid function. It could be just simple piecewise linear function. So the idea of the activation function here is that it adds some kind of nonlinearity. So we're not just stacking linear layers on top of one another, which if we were to stack linear layers on top of one another, then that's equivalent to just having a single linear function, basically. So you're just doing linear regression. But when you add some nonlinearity here, this is actually what gives your neural network more sort of expressiveness and the ability to actually model and approximate nonlinear functions. And so, as I said, we just take the summation of some coefficient, some parameter here, times the first input, some parameter times the second input, and some parameter times 1, and then we add them together, apply an activation function, and that gives us this value h1 here. Now, each of those circles here, each of those sort of input circles and The intermediate circles here, the yellow circles, are often called neurons in neural network or in deep learning. And so this first layer here has basically 2 input neurons, so we don't count the bias usually. So this has 2 input neurons, and then this first hidden layer or only hidden layer has 3 neurons, so H1, H2, and H3. And then the output layer here has just a single neuron, essentially. And so, again, the flow of the data, the way we actually sort of apply or evaluate this function. So if I give you x1 and x2, is you take x1, x2, and 1, multiply them by the corresponding coefficients, add the multiplications together, apply an activation function, then you get h1. Do the same thing but with a different set of coefficients, and then again you sum them together, apply the same activation function, and you get h2. Repeat that same process for h3. Again, each of those are all different coefficients, and then we end up with h1, h2, and h3. Then we can repeat the same process again, but this time for a new layer, for the next layer. And so for the next layer, now we need the bias term again, so we just bring this 1 in again. So 1 is always an input with us in every layer. And now we multiply it by different coefficients. So you see the superscript here refers to the layer index. So this is the first layer, this is sort of the second layer, and so the subscripts refer to what is the input. The first subscript is the input index, the second subscript is the output index. In this case, we only have a single output, and so the weights are all going to be W2 1, W2 to 1, W2 3, 1. So that's the second layer, and then the third sort of input, and the only output here. And the index of the bias term, again, we have the superscript is basically the layer index, and the subscript is going to be the output index for the bias term. So that's sort of, again, a very simple so-called perceptron or multi-layer perceptron, if you like, or neural network. Sometimes it's called a densely connected. So this kind of connection here is often called a dense connection. It's dense because every input is passed or is sort of assumed to influence every output. And so you see here like this full connectivity. And so often this will be called a dense layer, essentially. And again, there are different types of layers that can handle different data structures. So if my input here was an image, for example, then there are certain layers called convolution layers that can handle image data. And then you can, again, come up with more creative sort of layers, and there are different ways to connect the layers together as well. And so it gets a bit more creative than this, but that's sort of the basic building unit or building block. And you can already do a lot of very nice sort of approximations of complicated nonlinear functions using this very simple structure here, just by changing the number of neurons in the hidden layers or by changing the number of hidden layers. Now, how do we actually pick these inputs and hidden layers and outputs? That will depend a lot on the intended application that you have. And so let's say, for example, I want to use my neural network in some dynamics function to help with defining the differential equation of a scientific machine learning model. In this case, maybe I want to input some of the state variables, some random effects, and some time, for example, and maybe some input covariates. And so let's say the total number of inputs that I'm interested in is maybe 5 or 6. So then the number of inputs would be essentially 6. So I would need x1, x2 until x6. Now, let's say the output here is going to give me the rate of change of a neural ODE, and the neural ODE has 3 compartments. And so I would like, then the output has to have basically 3 outputs, or the neural network has to have 3 outputs in this case, because I have 3 compartments and I need to output the rate of change for each compartment. And so the number of inputs and the number of outputs will depend on the intended application and how exactly I would like to use this function. Now, the number of hidden layers and the number of neurons per hidden layer is often just a hyperparameter, or these are a couple of hyperparameters that we should basically tweak and tune until we get the nice or desired level of flexibility. So in general, if I increase the number of hidden layers and I increase the number of neurons per layer, I get a higher level of flexibility in my function. So my function is able to sort of morph and take the shape of much more complicated functions. And the neural network is known to be a universal approximator, and there are proofs for multiple activation functions that exist. And so in theory, if you increase the number of hidden layers to a large enough number, and you increase the number or even if you don't, actually just having a single layer with a lot of different neurons is usually sufficient to get that sort of desired behavior. But you can actually be more efficient in getting sort of complex behaviors if you also add layers. And so in general, if you increase the number of layers and also moderately increase the number of neurons per layer, you will get a very flexible sort of machine or function that has a lot of these parameters that you can then tweak and tune until you get the desired function behavior. And so again, that's sort of the main power of a neural network, is that it can approximate any kind of nonlinear function between x and y, which is why we're interested in it. So mathematically in matrix notation, we can put together all the weights here like this in this matrix form. So these are the weights from the first layer, and then we multiply it by a vector of all the inputs and then 1. And this multiplication basically is equivalent to the output of the summation here. So when we take the sum across all of these different weights, this can be written more compactly using this matrix vector multiplication. And then we apply the activation function to get H1, H2, and H3. So this is just a mathematical representation of what's happening down there. And then same thing here, but it's just that we have now three inputs and one output. And so we also have, again, the weights here laid out like this in one row. We have our 3 weights here for the 3 inputs, and then 1 is also this sort of shadow input that's always coming with us. And so the size here is going to be always 1 by the number of inputs plus 1. And then you multiply this by, again, the actual inputs, which in this case, the inputs are the hidden layer neurons, and then 1 at the end. You get the output of the summation, again, from at this point here. That's the same as the output of this matrix vector multiply, or in this case, it's just the dot product, really, of this row vector and this column vector. And then you apply the activation function again, and you get y1. Right? So it's a very simple recipe, and you can see that basically we can now stack this or do this process over and over and over again. So we can put this in a loop. We can have multiple weight coefficients or multiple matrices like this, and then just repeat this many, many times and have a neural network with perhaps 10 layers and 100 neurons per layer. And so it's actually quite easy to build your own neural network manually, and at least in the forward evaluation. And all usually the biggest challenge is then how you actually fit those and calculate gradients and so on, but we'll come to that. But in general, this matrix here will be called the weight matrix, or W, and often it will sort of be implied that it also includes the bias. And when we say weights and biases, then we use the term weights to refer to the W's, and the term bias to refer to just the B's, or the B coefficients here. But often you can just call them all weights or parameters, essentially. And these are all tunable parameters. So these are all like the coefficients in a linear regression model. It's just that we have usually a lot more of them because we have many of those layers, essentially. Whereas in a linear regression, you just have like a single layer. In fact, a linear regression model is just a one layer, like imagine there's no hidden layer here. We go from input to output directly, and it's just the activation function is a linear function. Or sometimes in generalized linear models, it would be something like the inverse of the link function, for example, or related to the link function. So the idea of linear regression and generalized linear models, most of these models can actually be mapped to to be a special case of a neural network. And so the neural network generalizes this by just having more hidden layers, having some nonlinear activation function that connect the inputs to the outputs. And you can still have your favorite link function here at the end. And so that means also the neural network can be used, for example, not just when your output is continuous, but you can use it even if the output is Bernoulli or is a binary random variable. So if y is binary, we would just be predicting essentially the logistic of the probability, and then you would, or rather the logit of the probability, and then you would just take the logistic of that, and that would give you the probability of your Bernoulli distribution. And so you can apply the same standard techniques for generalized linear models and handling sort of discrete data and different types of constrained data. Like if y here is positive, then we can just predict the log of y and then transform that directly using the exponential function. And so a lot of this stuff can actually be directly encoded as well in the activation function here. by just having a fancier activation function or a special activation function for the output layer. And that's commonly the case, where you can just this activation function for the output layer, you can define it to be any kind of function you want, depending on the desired domain of the outputs. If I want the output to be positive, then this has to be a function that outputs some positive number. If I want the output to be between 0 and 1, then this could be the sigmoid function or the logistic function, and so on. So the output layer activation function will often be slightly different from the rest of the hidden layers. So this is, again, the overall architecture of a multi-layer perceptron, especially with the dense layer. So that's one dense layer here, and that's also a dense layer here, because, again, all the inputs are affecting in this case, there's a single output. And so these are just two dense layers that we stacked on top of one another. Now, the goal when fitting this neural network is essentially to minimize some loss. Now, sometimes the loss will be directly derived using the output of the neural network. Sometimes the loss is a much bigger function. Like, this neural network is only part of your model, and your losses actually depends on the entirety of your model. And so it could be that the output here is coming from some other part of your model, the input here is coming from some other part of your model, and the output here is going to be used in another part of the model. And then the actual loss function requires a much more complicated evaluation of your entire model. Not this could be just a component of your model, right? And so you could think of, like, in more traditional deep learning, you're just using this to predict some quantity, and so you can define the loss directly using y, essentially. But in more scientific machine learning and nonlinear mixed effects modeling context, where we're going to be using the neural network, it's going to be a component of a model. And so you should really think of this as just a function that has a bunch of parameters. These parameters, which are all the weights and the biases, are going to be optimized or tuned along with all the other parameters of the model. And so these are just regular parameters in your model that can be tuned along with your typical values for different parameters like clearance and volume and so on, along with all of your omegas and any other parameter that exists in your model outside of this neural network. And so these are just regular model parameters. Usually they're just population parameters, essentially, that get optimized like all the rest of your population parameters. And again, in more traditional deep learning, which we'll see an example of, we define the loss directly, and like this is the entirety of the model. There is no other part of the model, and so we can actually define the loss directly using the output here, like using sum of square error or something like that. Good. So how do we actually train a neural network? Well, to train a neural network, you need to define your loss. In this case, we assume that the neural network is the entirety of the model, in which case the loss can be defined using essentially the output of the neural network, or the predicted output of the neural network, which we're going to refer to here using y hat. As y hat is essentially the predicted y here, which is just y1 in this figure before. And then x is just the input x, and so that could be a bunch of covariates like age, sex, weight, etc. And then for those given covariates, we predict, for example, whether that patient is going to respond to a drug or not. So this could be actually part of, well, that's a classification problem, but we could predict the probability or the logit of the probability, for example, that a patient is going to respond to the drug or not. And so we can take our predicted y here and sort of define some loss function, and this loss will be different for different sort of outcomes. If it's a continuous outcome, then we can just define the sum of square error. If it's some, again, sort of binary output here, y, then we can define something like the cross entropy, for example. So there are different losses for different data types, y here, whether it's discrete or continuous. But let's assume for simplicity that it's continuous and that we just define the loss as just a sum of square of the predicted y, essentially, and the actual value of y for a given x. And so for every input data point here, so I here stands for an input data point. For every input data point, let's say I have 10 subjects or 100 subjects, then the value of n here would be 100, and then I would take the loss by basically taking the inputs for each subject or each point, passing it through our neural network that we defined earlier. For each one of those inputs, or for each sort of subject or point, I'm going to get a set of outputs or predicted outputs. Then I can take those predicted outputs here and then take the loss between the predicted outputs and the real output yi. So yi here stands for the real output, and y hat here stands for the output of the neural network, and xi is the real input, is the actual observed input. Now, this uppercase W is just a set of weights or coefficients, which includes the weights and the biases from the previous slide. And this whole thing is basically becomes, like, you can think L here stands for loss. So you can often a terminology for this is a loss function per point or per subject. When you take all of this, or you sum all of these losses per point, you get the loss over your whole data set. Sometimes also called the cost function. So cost or loss. In this case, I'm using loss to refer to sort of the individual loss, and then C as sort of the overall or the sum of the individual losses, although these terms can be interchangeable. So once we have this cost function or loss function, now we would like to minimize it. The goal is to find, again, the weights here or the parameters W that would allow us to predict some relationship between xi and yi. Right? And so the best value of W is one that gives us, let's say, the minimum sum of square between these two. And so if I choose my L here, my individual loss, to be the sum of square, like which is this function here, then the best value of W is one that forces these residuals, essentially, these are often called residuals or errors, to be equal to 0, right? Now we'll discuss overfitting in a minute, because if you actually try to make it equal to 0, sometimes you're fitting the noise, or you're fitting some sort of unpredictable quantity in your data, which is different from one data point to the other, and that means that you're overfitting your training data. But ideally and intuitively, we would like this number to be as small as possible, assuming that there is actually no unpredictable noise, that everything is a perfect signal, sort of predictable signal. Then we would like this number to be as close to 0 as possible by tweaking and tuning this set of weights or parameters W. And the way we do this is often using some algorithm known as gradient descent, which is not unlike any algorithm used to train, for example, nonlinear mixed effects models. If you come from that, often in NLME, we also use a variation of gradient descent to minimize the loss. But the loss there is a bit different from just a sum of square error. It's often the sort of negative log marginal likelihood. But at the end of the day, the way we optimize it is very similar. In this case, we're using a variation of gradient descent known as stochastic gradient descent. And the way stochastic gradient descent works, or gradient descent in general, is by taking some gradient, or the gradient of our cost function with respect to W. Now, the gradient with respect to W is just the rate of change of this quantity, this cost function C here, with respect to W. In other words, it's a vector that's going to have the same shape as W, or a matrix, that tells me how sensitive. So if I change W11 here, how sensitive is the loss to this change in W11? And so if the loss is very sensitive to this change, if I increase W11 and in the first layer, and the loss increases a lot, then that means this here is quite sensitive, or this is quite important. And so the gradient, or the corresponding derivative in the gradient, will be high. The corresponding value of W11 of the first layer in that gradient vector will be large. And if W11 does not contribute at all to the loss, if changing W11, increasing it or decreasing it, doesn't really change much in the loss, then the derivative will be very, very small. So the derivative is just the rate of change of the loss function, not this output. It's actually the loss function, which in this case is the sum of square of the output of the neural network and the real data, how sensitive that is to each of the individual weights, right? That gives us the gradient vector. And again, if we increase W11, and y1 increases, or sorry, the loss increases, not y1, then the derivative will be positive. If we increase W11 and the loss decreases, then the derivative will be negative. And so the sign of the derivative depends on whether W11 has an increasing effect on the loss or a decreasing effect on the loss. Now, because this here sort of tells me then how sensitive how sensitive the cost function is to each of the weights, and it tells me, like, if a value is large, that means increasing it increases the loss. then I take the negative of that and I multiply it by some small coefficient, usually 0.1 or 0.01 or something like that. And then I go against the direction of the gradient, because going towards the direction of the gradient will increase my cost. And so I would like to minimize the cost by going against the direction of the gradient. And the way I do this is by taking a so-called step size, or a small step. So this is often called a step size. So I take a step towards the negative of the gradient. So this here times -1, and then I take some small alpha or some small step size and multiply it by that, and then I use that to update the weights. So the new weights will be my old weights, which can be initialized randomly. So there are many different ways to initialize these weights. And then minus some small alpha, some small step size, times the gradient of the cost function with respect to the weights. And this sort of overall, this very simple recipe, there are many variations of it again that have been invented over the years. But this very simple recipe should already give you some optimized or help improve the weights from, like, let's say some random weights. If you follow this and you repeat this over and over again, so now after we update the weights, we go back and evaluate the gradient again at the new weights, and then update the weights and go back and evaluate them and update the weights, etc. So if you just keep alternating between evaluating the gradient and doing some update of the weights, we will eventually get to some coefficients or weights that actually give us a pretty low value for this loss function here. And that's sort of the basic idea. Now, there are more efficient variations of stochastic gradient descent or gradient descent in general, and that's what we use in practice, but this is sort of the basic idea, and they all have a very similar basic idea. Now, so far I've been describing really actually gradient descent in machine learning, in deep learning. It's common to use stochastic gradient descent, where the stochasticity just comes from not summing over all of the subjects, essentially, but only taking a subset of the subjects or a subset of the points and then using them to evaluate the gradient. So instead of taking the gradient for all the data points, if I have too many data points, like billions of subjects or billions of points, then this can be quite inefficient. And so it is common practice in deep learning to then just take a subset, often called the batch, of your or a mini batch of your data, and then you calculate the gradient just using this mini batch. And you need to do some scaling tricks as well if you have regularization and so on. But the idea is that you by doing this, you can actually get some rough idea about where the gradient is heading, without having to evaluate the cost for all your data points, which if you have billions of data points, maybe I only need a couple of hundred points to actually tell me how to improve my loss. And then you hope or you count on the fact that as you alternate, every time you evaluate this, you're actually using a different subset of points, and then over time that actually ends up still improving your global loss. The global loss becomes, or the full batch loss is the sum of the losses for all of the points, not just your mini batch points. And that's actually what we want to minimize. It's just that to minimize this, sometimes it's convenient to just take a batch or a small subset of your points and minimize using just those subset of points in every iteration. And in every iteration, you take a different subset of points. Now, another advantage of this stochastic gradient descent is that it adds some randomness to the optimization process, whereas if you do more classical gradient descent methods, they tend to be deterministic, meaning they're if you evaluate them using the same initial sort of W, and then you do 10 iterations, you get to the same final W after the 10 iterations. With stochastic gradient descent, if we actually have we enable some randomness, for example, by shuffling the data points or by taking a random set of data points in every iteration. That actually introduces a little bit of randomness in the process, and that randomness is often useful in avoiding certain local minima, in sort of pushing you away from getting or lowering the chances of getting stuck in certain local minima. Now, it does have a disadvantage of actually slowing down convergence. Often, full batch methods will have a better convergence rate, for example, in terms of the number of iterations. And so with stochastic methods, you often need more iterations to converge. But the idea is that the trade-off is worth it because you also get a little bit of randomness associated with that. And you can also, if you use a large enough batch size, then the convergence rate it tends to be quite good, or it's not too bad. But also the randomness added can actually end up giving you overall better training results, because you end up not getting stuck or not when there's randomness involved, you're more likely to nudge your point away from certain local minima, and so you have more exploration power, and it explores a bit the parameter space a bit more than when you do deterministic. With deterministic, you're basically at the mercy of the initialization. So if you initialize the weights correctly or well, then you might get to a good solution. If you initialize the weights badly, then you might get to a bad solution. And often there is also like different ways to go about this. For example, I can use deterministic optimization, but with multi-start. So I can use multiple different initializations here, and then each of them I can do a deterministic fit or deterministic training, and then pick the best at the end. And so there are different ways to approach this, but when you have a large data set, a stochastic gradient descent or some variation of that, often called the Adam algorithm. Adam is a variation of stochastic gradient descent. It tends to be used in practice quite a lot. Good. Now we've seen that the loss could be essentially or often, like intuitively, you may want to minimize the sum of square error here. Now what I would like to show you is that this sum of square error is actually sort of a special case of another loss that's called the negative log likelihood. And so if I assume a certain normal distribution, if I assume that my yi here is normally distributed with a mean y hat, which is the output of the neural network, and some variance sigma square here, then by taking the log probability of this, or the negative log probability, I get this expression below. And then by setting the sigma square to a specific value, I actually get this expression here. Now this expression is nothing but a constant plus the sum of square error. Right, so I recover back my sum of square error loss as a sort of special case of the negative log likelihood, which is sort of more commonly used also in different contexts in statistics. Sum of square is also used to get unbiased estimators and so on for linear regression. But the log likelihood or maximum likelihood estimation is often easier to apply to things like discrete data as well, and where we can have allows us to use arbitrary distributions here depending on your data type, and then it naturally extends to all these different data types. And so maximum likelihood estimation, or minimizing the negative log likelihood by maximizing the log likelihood, it's equivalent to minimizing the negative of the log likelihood. We actually show here that it's equivalent essentially to minimizing the sum of square error for a special choice of sigma square. So you have to fix sigma, and then you get this constant here that you can drop from the optimization. Because it's a constant, it doesn't actually, when you take the gradient of this, the gradient of this is going to be 0 with respect to all of the parameters of the neural network. So that means that basically instead of minimizing the sum of square error, what we could do, which we often do in a PUMAS model, is just define a distribution for y. Define like a normal distribution for y. Often we call this the error model in the context of pharmacometrics and nonlinear mixed effects modeling. But here we don't really have random effects at all. So you can think of these as just some population parameters essentially, and there are no random effects. It's just a single subject model or naive pooling, let's say. And then we have this function y that takes the parameters w and takes some input x and outputs some value here that's actually the mean of, or they're going to be the mean or the individual prediction of a specific subject. And then this here is the actual observation yi that's assumed to be normally distributed with this specific mean and some sigma square. Now I can also choose to fine tune or to train sigma square simultaneously, and that's commonly also done even in things like linear regression, although you might get a little bit of biased estimation here, but it's a consistent estimator. But the idea is that you can basically fit both W and sigma squares simultaneously by just doing this maximum likelihood estimation, or maximizing the log likelihood or minimizing the negative of the log likelihood as your loss function. And that sort of nicely generalizes the idea of the sum of square error, but then it allows us to then define the things directly using distributions, which is a bit more intuitive. And so if my yi is positive, I can just define this as a log normal distribution. Instead, if my yi is between 0 and 1, I can use a beta distribution or a logit normal distribution. And so by defining different distributions here, the log likelihood or the negative log likelihood naturally becomes our loss function, and we don't need to worry about the actual derivation of that loss anymore. We just define the distribution, so it's a nicer, sort of higher level of abstraction that we can think in terms of, which allows us to not worry too much about the actual specific loss function definition. Good. Now, let's say we do train. So I mentioned before that the goal is to actually minimize this and make it as close to zero as possible. Let's assume again that we have a sum of square error as a loss, which is good for just reasoning and thinking about it. And so in that case, you could think that the optimal solution would be one where I can pick the values here for the weights W or the parameters W such that this is exactly equal to yi, and that means I have basically a perfect fit. So I'm going through every single point. I'm fitting every single point perfectly. But what ends up happening then is if I actually take some data or some new data, let's say, comes in and that hasn't been used in the training, and then I try to evaluate the loss on this new data without training on it, I'm just evaluating the loss, you will see that as I keep training and as I increase the model complexity, and you can think of the idea of model complexity is that, let's say if my model here is able to fit the data perfectly, right? And so if the data here has some noise, for the model to be able to fit the data perfectly, it has to go up and down quite a lot. It has to sort of be extremely flexible, be extremely complex. And so the weights W here have to be tuned quite a bit to make sure that we get these perfect weights that go through every single point. And so think of this as sort of as we're training the model more and more to minimize the sum of square error more and more across the different training points, we actually end up with, at some point, the test performance gets worse, right? And that's because we're fitting the noise now. Like we started by, let's say, some random weights here. And so when you have random weights, you're doing pretty badly on both the test set and the training data, right? The test set, again, is left out from the training. It's just used to evaluate your model after the training or as you're training it sometimes. And so you start from these random weights with pretty horrible performance on both the training and test data. But because the weights are picked randomly, the data is picked randomly, data splitting is randomly assumed in this case, we assume that that's the case, then you get very similarly, like let's say per point errors, like that. This is like the error per point would be similar between the training and the test, because the data has not yet been used to actually train the model. Now, as you train the model, you start noticing a drop or an improvement in the performance, so your prediction error is actually decreasing for both the training and the test data. And that's because your model is actually learning some nice signal from your data. So if your data follows some y equals x squared function, then your model starts taking the shape of a quadratic function. And slowly you end up getting better performance, at least better compared to the initial random weights. But then at some point, you start not just learning the signal, which is the quadratic function, but also learning things like the noise, the individual noise terms. Now, those noise terms or the individual noise should not be predictable. By definition, noise is unpredictable, and we assume that there's always this component of noise that could be dependent on other factors that we never observed. Could be like, as far as we're concerned, they're random, but that randomness could also imply that they actually are predictable, but they depend on things that we haven't really measured. They depend on things that are not in the inputs that we have here. And so as far as we are concerned, we can treat them as just random, essentially. And because they're random and because they're not predictable from the inputs, that's the assumption here, then by predicting the noise and by making sure our model is able to fit that noise for the training data, we are by definition making our model sort of super customized to the training data and not really able to generalize to a new data set, because a new data set will have a different set of noise terms added to each point, and that's by fitting the noise of the training data, we're basically compromising the performance and making it worse on the test data as a result. And that's sort of intuitively what we're doing here. And so we're fitting too much, basically, the points in the training data. And as a result, we're not able to generalize nearly as much to the test data. And what that usually means is actually we're able to, we end up having sort of a higher variance as well in the in the performance. And so if I have a new data point or a new test set coming in, I can get, let's say, a certain prediction error, and then another test set, I get another prediction error per point, and that prediction error per point will generally have a high variance. Sometimes I will be perfectly fitting every point, and sometimes I will be completely off, basically, because my model is too complex. My model goes up and down quite a lot. It fluctuates a lot, and so it has a much higher variance in the error. Let's say every time I get a new test data or a new data point to predict on, the loss that I get, if I plot the variance of those, or if I calculate the variance of those, that variance will be quite high as a result of this overfitting behavior. And so this kind of phenomena is quite common, and you'll see in the tutorial that we're actually able to reproduce a graph that looks like this using a specific Pumas model or DeepPumas model. But that sort of gives you an idea of what to expect when you train your model for too long, or you train a model that has too many layers or too many parameters, or if your data is actually quite small. So if your signal is very simple, like you just have a linear function, you only have 2-3 points, and it's pretty visible that it's linear. It's pretty obvious if you just plot them that it's linear, the relationship between the input and the output, then using an overly complex model will actually end up hurting you at some point, unless we do something about it. So we'll see what we can do about this kind of overfitting behavior. Okay, but before we do that, let's maybe recap some of the stuff that we talked about. And so we mentioned that, like, so far what we've seen is actually a specific architecture of a neural network, often called a feed-forward neural network or a dense neural network. And here I'm assuming that I'm just ignoring the bias terms or the ones just for simplicity. So we have these inputs that go into some hidden layer, and then the hidden layer go into the output, and the goal is to then make sure that the predicted output is as close as possible to a specific target Y, right? So that's sort of the summary of what we discussed so far. And the basic interface is the number of input units, as we said before, the number of outputs, and those will be application specific depending on how many input covariates you have, for example, how many inputs you would like to use in the neural network, whether it's time or random effects or compartments, for example, like dynamic variables. This will all determine the number of inputs to your neural network. The number of outputs is determined by how I would like to use that neural network. If I'm using it as the rate of change of a neural ODE with 3 compartments, then I need 3 outputs. If I'm using it just to predict Y directly, then and Y is just a scalar, then maybe I just need a single output. And so depending on how it's actually used, then the number of outputs will be also determined. The activation function of the output layer, we discussed that this will depend a lot on the domain of the output as well. And so if the output is positive, then I would like an activation function that only outputs positive numbers, because by default, the summation here that we saw, when you take these weights are unconstrained, right? And so when you take these weights here, you multiply them by some values here, you could get, and then you sum them together, you could get either positive or negative values here. There's no restriction on the sign or the domain of the summation. And so the restriction has to then come from the activation function of the output layer. And so that's another key sort of consideration when you're designing these neural networks, is to think, what exactly should I use for the output layer's activation function? And generally speaking, it doesn't have to be the same as the hidden layer activation functions, because that's much more sort of domain specific, whereas the hidden layer activation function tends to be less important. Like, we can use multiple different functions there, and you get the desired behavior, which is the universal approximation behavior. Although sometimes they can also have an effect on the output. The architecture, we generally try to select it carefully, although again, like, this is just a hyperparameter, and one could always try to increase them and see basically when you start getting diminishing returns. And so often it's not a bad practice to start from something small and then see how much of a performance you get. Even start from a linear function, basically just a single layer, like no hidden layers at all, just a simple sort of linear regression model or generalized linear model with maybe a nonlinear activation function if you want, just to match the domain of your output or the desired domain of the output. And then you see what you get as a performance from that, and then you start increasing the complexity gradually, and you evaluate the performance on some unseen data. You always use unseen data to evaluate the performance, not the training data. And then you can see, is there actually any benefit from adding more hidden layers or more units per hidden layer. And then the activation function for the hidden layers, again, that's another hyperparameter that you can try a couple of different functions and see which one tends to work best for your application. Often it can be difficult to guess upfront which function is actually going to work better. Some functions have some problem called vanishing gradients. Some function can give you something called exploding gradients. And so each function will or set of functions will have its own sort of trade-offs there as well. And there are many different choices of activation functions, which we might cover in a future slide. Then finally, we have the actual optimization algorithm that we would like to pick. So we discussed gradient descent or stochastic gradient descent. And we said that sometimes also we can use deterministic algorithms, maybe with multi-start, to give us a bit more robustness to the initial point. But the specific optimization algorithm is often also a key consideration that we need to think about. Now, as a user, let's say if you're using Pumas or DeepPumas, we already sort of have some default optimization algorithms, but it might still be useful to do multi-start manually by randomly sampling the weights and then restarting the optimization. The activation function is something that you would have to pick yourself, although again we do have some default values. The number of units per hidden layer is something you have to pick, the number of hidden layers you have to pick, and obviously the number of outputs and inputs and the activation layer of the activation function of the output layer are all things that you have to actually select when you're working with neural networks in DeepPumas. Good. Now, the activation function is, there are many choices for activation functions as we discussed before. And so the output layer, we can either use the identity function, which is just f of x equals x. So it's actually like not having an activation function at all, just the input is passed directly as the output. And that's common for certain regression tasks where the output is expected to be unconstrained. So whether it can be negative or positive, basically, there's no restriction on that. Then it's common to use the identity function as the loss in this case. And again, that's similar to how you would do linear regression, for example, with maximum likelihood estimation. You can also just apply the identity function and just like if you basically have no hidden layers here and have the identity function as activation function, then that becomes a linear regression model. Now, another common function to use is a sigmoid function, which allows us to take the output from the last layer and then, which is unconstrained, and then transform it to an output that's between 0 and 1. Now, because it's between 0 and 1, we can actually use it as the probability of a Bernoulli distribution and then use it to define a Bernoulli distribution for my data. Now, we said that we're going to be using the log likelihood from now on, and so I can just define this as a Bernoulli distribution for my data, and then the output of the neural network will be between 0 and 1, and I don't have a sigma square anymore because the Bernoulli distribution has a single parameter, which is a probability parameter between 0 and 1, and so the output here can be between 0 and 1, and I have no sigma square, and that could be a Bernoulli distribution. And that's how you would define then a classification model, like a binary classification model using neural networks. And the loss function will just be the negative log likelihood of the Bernoulli distribution, which is the same as the cross entropy function that's commonly used in deep learning as well. So there's sort of this one-to-one mapping between a specific distribution and the specific loss functions that people commonly use in deep learning training. But again, it is more natural to think about distributions usually than to think about the actual sort of mathematical functional form of the loss or the coast function. So sigmoid function is quite common in that. The softmax function is a function that generalizes the idea of a sigmoid, and it gives us essentially multiple different values between 0 and 1 instead of just a single value between 0 and 1. So it's a function that takes, let's say, n inputs and then gives you n outputs. The n inputs will be unconstrained and the outputs will be between 0 and 1, and they sum up to 1. And so they all represent like essentially multi-class probabilities. So the probability of class 1, probability of class 2, etc. And then the sum of them is equal to 1. So we can use the output of this softmax function to pass then to a categorical distribution and then construct a categorical distribution for our data point or for our observations. And so softmax is sort of a nice generalization of the sigmoid function to multiple dimensions for when we have multiple classes in our classification task. And then there's the soft plus function, which is just a nice function that has positive numbers only as its output. And so it, again, takes input that's between negative infinity and positive infinity, and then it outputs a number that's only non-negative, that is strictly sort of, usually it's strictly above zero, but then due to underflow problems, it can also be sometimes zero, at least represented as zero. But the number will never be negative, and that's useful when you have, let's say, certain outputs that can only be positive. So if you're using the output of the neural network to define some perhaps instantaneous hazard function, for example, that you're then integrating over time, then you would like that instantaneous hazard function to be positive, which is then can be used for a time to event model. And so that's, again, bringing us back to this idea of the neural network being just a component of your model. And the most interesting uses of neural networks that we will see are actually going to be when the neural network is only one component of the model and not the full complete model. So the soft plus function is useful. You can also use exponential, but sometimes exponential has problems when the values get too large. If the inputs are too large, then exponential will give you a very large number. And if the inputs are too large negative, on the negative side, then the exponential function will underflow very quickly and give you basically something very close to zero. And so the soft plus, you can think of it as sort of a nicer version of the exponential function, or alternative to the exponential function, that has nicer numerical properties. When you don't actually care about exponential for some, like, let's say, domain-specific reasons, and you just want the positive, like any function that takes unconstrained inputs to be and gives us positive outputs, then you can use the soft plus instead of the exponential. This will often give you better numerical, like less or higher numerical stability in your fitting and simulation and so on. Now, in the hidden layers, you can use, again, any kind of activation function, but some of the most common ones are sigmoid and tanh. At least that's the default value is tanh in DeepPumas for the hidden layer activation functions. Now, deep neural networks or any kind of really neural network can often suffer from something called the vanishing gradient problem, which we will cover in more details in the future, but it basically refers to the problem when the activation function has sort of a flat or a plateau at some point. So it could plateau when the value of the input is large, or plateau when the value of the input is sort of a large negative number. And when that plateau happens, you get basically zero sensitivity. So by changing some of the weights, it has no effect on the loss as a result, because it doesn't matter. It changes it a bit, but it actually, the change is so small that it's not something we can easily detect numerically. And so when that happens, you get something called a vanishing gradient, which is basically forces you to get stuck in a bad local optimum. So you might just, like, you're more likely to get stuck in a bad local optimum when you have this vanishing gradient issue, because the gradient is zero. You're technically at a local optimum, it's just that it's not a very good one, or there are many such local optima that are not good that you can easily get stuck in if you end up sort of tweaking your weights a bit such that you have this vanishing gradient, or tweaking the input such that you have this vanishing gradient. And so for that, often it's quite important to scale all the inputs appropriately, make sure that the scales of the inputs are not too large in magnitude, so positive or negative. So input scaling is quite important to avoid the vanishing gradients, and we will see perhaps more examples of this in the future. Good. Again, by default, we use tanh. If you want, you can also explore this ReLU activation function if you suspect that you're getting stuck in a bad local optimum. Often the ReLU function can help you test for this. And ReLU has its own set of problems sometimes, which is that you may not actually get the gradient, or the gradient would not be getting close to zero sometimes. And so you have this sort of, again, ReLU is a discontinuous function or has some sort of non-smoothness, not discontinuity. It's a continuous function, but it's non-smooth. And so it can have some other kinds of effects when using smooth optimization algorithms. So each of those activation functions will tend to have its own sort of quirks. And so it's often useful to try maybe the default first. If it works, great. If it doesn't work, then try switching things out and essentially treat the activation function as a hyperparameter and just try a few of them and see which one works best. Good. So we've been talking a lot about hyperparameters. That includes the activation function, includes the number of layers, the number of neurons per layer. And so often hyperparameter optimization happens. There are many different algorithms to do hyperparameter search. You could do just a simple grid search where I just try basically different values in a grid. So I try maybe two layers, 3 layers, 4 layers, hidden layers, of course. I always have one input and one output layers. Those are non-negotiable. But I could have 2, 3, and 4 hidden layers, and then I could have, let's say, 3 neurons per hidden layer, 4 neurons, and 5 neurons. And so I could try different sort of combinations of these parameters that I suspect are important, and then pick the best by some definition of best. Or if 2 are basically equally good, then I can pick the smaller one just because it's cheaper and easier to compute and train. Or you could also just do a random search, basically where we just pick some random points in the search space and then we try them out and see which one works. And there are much more intelligent ways to do this using something called Bayesian optimization, which tries to be, it's random, but it tries to be a bit intelligent or smart about where the next point to try is. And so it tries maybe first 1 or 2 points, and then based on the results you get, it tries different other configurations based on, again, some model that it fits, and tries to balance between exploration and exploitation. So it has quite a lot of details, but the idea is that it's like a random search, but somewhat guided towards the areas that tend to have good performance. And of course, there are sort of also multiple competing objectives here. So we care too much about the performance, but we also care about computational speed and how fast the model is to evaluate and train. And so often it's one not such a bad idea, or one strategy that works pretty well in practice is you just start from a small configuration and then you try increasing things and seeing if you get an improvement. So increase maybe the number of layers, see if you get any improvement that's significant, and if you don't, then just go back and don't actually apply that change, and then apply another change like increasing the number of neurons per layer, and again seeing if you get an improvement. And if you want, you can also do both changes at the same time as a third data point, and then if you don't get a significant improvement, then just conclude that this point here is sufficiently good. And you might get a slight improvement, but then you think it's not really worth it because it doubles your compute time, but the performance is only maybe 1% better. And so there are usually different sort of trade-offs that means that maybe doing this sort of manual hyperparameter tuning is often, or doing some sort of, like you can write your own function, let's say, to encode your own trade-offs and your own, like how much you actually care about, let's say, gains in performance versus gains in compute time or runtime. If you have a very large data set, a very complicated model, and modest compute, then often you care a lot about compute time and not just about sort of the raw performance you get, like the statistical performance or in terms like the accuracy of your model, essentially. And so there are many of these techniques for hyperparameter optimization. I personally prefer the more manual one, unless the model is quick enough to fit. Then you can do some more automated hyperparameter search. And for that, there are, again, as we said here, a couple of different techniques. Now, there are cases when the automatic one is the preferred. Again, if the model fit is not that slow. And often that's the case, for example, if I'm doing some regression, some linear regression or nonlinear regression, or doing some classification, then often the compute, the training, if the neural network is not huge, it can be quite fast. And so we can do this automated hyperparameter search, and we have this done or implemented for you in DeepPumas. But if when I'm using the neural network, let's say as part of a nonlinear mixed effects model, and then it's actually part of a dynamics, or like a stiff ODE that has a neural network as a component of it, and then that's part of a bigger model that's a nonlinear mixed effects model with a lot of parameters and a lot of subjects and so on, then often the fit of the model can take hours, and just because the fit takes that long, sometimes doing the hyperparameter search more manually tends to be a bit more cost effective, cost in terms of actual dollars you have to pay for compute. And so often that could be a bit preferred in that case. If you have obviously a lot of compute and parallel compute power, then just do like 1,000 different runs at the same time, and maybe do like either the grid layout or do a random layout, and just try 1,000 different configurations and then compare them at the end and see which one is the best given any of the criteria that you have, which is often, let's say, the performance or the accuracy on unseen data, as well as how long it took to actually complete, let's say, finishing a set number of iterations. There's a lot more to say about architecture search and hyperparameter selection, and we will sort of revisit this again in the actual case the tutorials that we have. But that gives you some basic idea about what the different strategies available are. Hopefully. So we discussed that the concept of overfitting, but then the concept of underfitting is basically just the opposite of that, where we before basically let's say we're fitting the model here for many iterations, and then at the beginning of a fit, let's say after just 0 iterations or 1 iteration, our models are usually still underfitted. So they're not fitted to the data, they're not fitting the signal in the data correctly. It's just some random function basically depending on the initialization. And so that's often called underfitting. And then if you end up fitting to the training data way too much or for too long without any restrictions, then you end up having a very small sum of square error for the training data, but then the test data performance tends to suffer. And so that is usually an indication, or that's the definition of overfitting, when you start fitting the noise of your training data and not just the signal. And when you fit the noise of the training data, you always usually get some drop in the performance or increase in the error in the noise or in fitting essentially the test data. And so you have this sort of increasing behavior here for the prediction error on the test data and decreasing behavior for the prediction error on the training data. And that's again because you're fitting the noise, which is what's often called as overfitting. Now, there are a number of strategies or techniques to prevent overfitting, or at least reduce the chances of overfitting. One would be just early stopping. So you can basically, every 10 iterations or so, check the performance on some unseen data, try to produce a plot that looks like this, essentially. And then when you notice that the test performance is actually getting worse, then you can go back and just pick the point where the test performance was optimal. So you're picking the number of iterations, you're treating the number of iterations of the optimization as a hyperparameter, and you're picking that hyperparameter based on the performance of your model on the test data, on the unseen data. Now, this is more often than would be called a validation data. So once you start using your test data to actually pick some hyperparameters, then it's no longer called a true test data, because true test data should be unseen, completely unseen, sort of unpolluted, unused by our model or modeler to select a model or to select any hyperparameter. And so often in that case, this would be actually called validation data. And you can think of it as just the data set that we're using to validate our model to make sure that we're not going completely off the rails here by overfitting our training model. And so you can basically keep going. So replace model complexity here with number of iterations, and you'll notice a very similar behavior as you increase the number of iterations. You will see that the training data, the training performance or loss is decreasing, but the test loss or the validation loss, at some point it will reach some local minimum here that you can then just pick. Now, sometimes you'll see that it reaches a minimum, then maybe it increases, sometimes it would drop again at some point, and so you may not notice a clean, or it may not be sort of a clean quadratic or clean local optimum like this, but then you can just pick sort of a reasonable points based on personal judgment. Just look at it and see, okay, maybe at this point it was good enough, or maybe there was another point here that's slightly better. And so again, usually in practice these curves don't tend to look as clean like this, and there may be some judgment call that has to be made as to whether to pick a point here or some other point here that might have very similar performance. Good. So that's one common technique, and it's quite easy to do. You don't need to do anything else. Just make sure that you keep some logs or keep some track of your training data or training performance and validation performance, and then pick a point or pick a stopping point based on that. Good. Now, it is quite important to do careful data splitting to avoid some data leakage. So what that usually means is that your training and test data should really be this different data sets. So I should not be reusing my training data as some validation data, for example. I should not be, let's say, transforming my training data in some way and then using that as the validation data, right? So these should really be independent, essentially. If they're not independent, if the test data or the validation data is just a simple transform of the training data, for example, or there's some shared data points or shared subjects between them, then that's often called as data leakage, which is the, again, process of using some of the training data as a validation data and then saying, okay, now this is now an unbiased or sort of like this gives me an objective metric of how good my model is actually performing on unseen data. So we're claiming that this is the performance on unseen data. So therefore, this should really be unseen data. Now, if this data was used in any way before in the training data or in the process of the training or in even the pre-processing of our data, sometimes a common mistake would be to use the validation data to even pre-process my training data. That can technically qualify as data leakage as well. And so it's quite important to make sure that whatever data you use to evaluate your model should be completely different or independent from the training data and should not be used to train the model in any way and should not be used to fine-tune the model or pick any of the parameters in the model. So data leakage is a very important consideration, and sometimes it can be can trip even more experienced machine learning practitioners. Now, the neural networks, we said that often compute like the cost of compute and the runtime is quite important, and we would really not like to use a neural network that's larger than it should. And so it's not a bad idea. It's not a bad idea or a bad strategy, especially if your data is sparse, which it often is in our domain in pharmacometrics. The data tends to be quite sparse. It's really not a bad idea to start with just a simple linear model and then slowly actually add complexity and then evaluate the gain that you make out of this additional complexity, and then stop when you stop making any, like when you have diminishing returns or you stop making significant improvements in the accuracy. And so the neural network should generally not be too large. Now, when the neural network is not too large, also that reduces the chances of overfitting. And so that's generally a nice strategy, not just to save compute, but also lower the chances of getting overfitting. Obviously, a large data set is always desired and can help also reduce the overfitting. So generally, the larger the data sets you have, the larger the neural network that you can afford without risking overfitting too much. But again, that's not something that we usually have the luxury of in our field in pharmacometrics. But if you do have a lot of data, then by all means use it. It's always a good idea, and more data always helps reduce the chances of overfitting. But this more data should not be, again, just simple transformation or augmentation of existing data, because that can actually sometimes, depending on how you do the augmentation, increase overfitting rather than decrease it. And it can make the performance on the unseen data actually worse rather than better. And so this here has to really be different independent data points, ideally, and not just simple transformations of your existing data. Although that can sometimes be helpful as well, just simple transformations, but that's a separate discussion. Now, by far the most common technique to prevent overfitting is this so-called regularization, which is to basically add some penalty to the cost function. That's usually the most common way of applying regularization. There are other methods to regularize, like, as I said, data augmentation, which if you do it carefully, it can help you actually reduce the chances of overfitting. But if you do it carelessly or in a bad way, can often hurt the performance of your model on the test data. And so data augmentation is a pretty important topic, but we're not going to go into too much details here. Adding something called the dropout layer. So a dropout layer is essentially indirect regularization. So remember, here in our neural network, we have these different hidden layers. There is a hidden layer that's often called a dropout layer, which basically just uses or turns off some of these neurons randomly when you're evaluating the model in feedforward, and when you do that, it will scale appropriately the remaining neurons. But when you do that, you're basically asking the neural network to be more robust to which of the hidden neurons here are actually active and actually contribute to the prediction. And so by adding this redundancy, it indirectly has the effect of also reducing overfitting and regularizing your model. And this has been shown empirically, that adding some so-called dropout layer, it might seem like an arbitrary idea, but you can actually show that this does help and does have a regularizing effect, essentially, when you do that. And it has been linked also to things like variational inference and Bayesian methods and so on. And so it again may seem like an ad hoc trick, but it actually does have quite a bit of theory behind it. But by far, when we say regularization, we actually just mean adding a penalty to the coast function. These other methods are sort of indirect ways to regularize. You can also think of the stochastic gradient descent, the stochastic optimization, as one way to prevent overfitting as well. When you're doing this stochastic optimization, you're less likely to sort of fully optimize to one Bayesian of attraction. So if I have a local minima that's really, really good, it's unlikely that I'll be able to actually hit that point when I'm doing stochastic optimization. So I'll be jumping around, let's say, from one sort of Bayesian of attraction to another, or from one local minima neighborhood to another. And by jumping from one neighborhood to another, I'm getting a bit more exploration, and there is less likely, or there's a lower chance that I will overfit, although it's still possible. So there are many techniques to try and reduce overfitting, but perhaps the most interesting for DeepPumas users would be, and maybe ones to try, would be this early stopping based on withheld data, and some regularization, which is again automated for you, as well as just trying small neural networks as much as possible. So these are maybe the most common techniques that we tend to use in DeepPumas. So let's talk a bit about the penalization of the coast function and how we can actually do this penalty. And so the one common penalty is to just take the LP norm of your weights and add it to the loss. And so I have here my coast function, which could be the sum of square error, could be the negative log likelihood. So this coast here could be whatever cost function that's defined for your data set and for your model that we defined earlier. So earlier we just defined it as the sum of square error. Essentially, for across all of our data points. Now, what we can do is just take some constant lambda here, which is often called the regularization strength or the penalty, and then we multiply it by the norm of the weights. And so what this means is we're basically saying we would like these weights to be as close to zero as possible. So this weight here can be positive, can be negative, and the norm here is minimized. So if you just try to minimize this norm here, this will be minimized when all the weights are set to zero. Now, if you think all the weights set to zero means that you have the zero function, like the output is always going to be zero. And so that's a very, very inflexible model, right? It's just a model that no matter what the input is, always gives you an output of zero. And that's sort of the optimum of this. And so the idea is that we don't want to minimize this, but we just want to add it as an additional penalty to try and drive these weights to be smaller than they would otherwise without the penalty. And then by controlling this value of lambda here, if I crank up lambda too much, if I increase lambda too much, then I would like my optimization algorithm will focus more on minimizing this than on minimizing the sum of square error or improving the prediction performance. And so these two are basically competing objectives, right? I could try to minimize the sum of square error too much and then ignore this penalty. And so the weights will be whatever they have to be to make this zero, basically. The minimum value of this is going to be zero. But that's most likely going to be an overfitted solution because the predictions are exactly equal to the observations. And that includes, again, some noise component that should be unpredictable, should not be predictable from X. Therefore, we know that we're actually overfitting. And so this could be driven down to zero and ignoring this, or we could drive this to zero and ignore this, right? Now, in the first case, we're overfitting. If we drive this one to zero and ignore the penalty, we're overfitting. In the second case, if we drive this to zero and ignore the cost function, then we're underfitting because we're getting basically the model that's always predicting zero. Always predicting zero, that's not a very good model for most of your data, unless your data is actually always zero. And therefore, you're underfitting. And so we have this term that encourages overfitting and this term that encourages underfitting. And then the idea is we can pick the optimal lambda that would give us the sort of optimal performance on unseen data. And so we can use the unseen data now to actually pick the value of lambda. So we can treat lambda just as a hyperparameter, try different values of lambda, and then train using the training data and using this loss here. and then evaluate the final model using the validation data, and then pick the value of lambda based on that. And so lambda here is called the regularization strength. And that's sort of the common way to do regularization in deep learning when you have some arbitrary cost function here, whatever this cost function is. But it's usually, again, depends on the data type that you have and depends on your model. And then we can add some penalty to it. And again, this here is often called so actually without the power p, just this is often called the LP norm, and then we often take the power p of that. The most common choice of p is actually p equals 2, or we just take the basically square of the L2 norm of the parameters, which amounts to just the sum of square of the weights. So when p equals 2 here, this is just the sum of square of all the weights, right? So I'm trying to drive down the weights to be as close as possible to 0, and in doing so, I'm reducing the chance of overfitting and also encouraging underfitting, essentially. So again, a common choice of p here is equal 2, but you can also use p equals 1, and p equals 1 will have some like sparse maintaining effect. Actually, p equals 2 tends to destroy sparsity, whereas p equals 1 is a bit more neutral to sparsity, and so it tends to have, compared to p equals 2 at least, a less destructive effect of sparsity. And so when you use p equals 2, you end up with very small, like most of these weights are going to be small and close to 0, but not 0. Whereas if you use p equals 1, you're more likely to get weights that are actually equal to 0. And not just close to 0. And so it tends to have a slightly sparsifying effect as a result. So those are two common choices of p. Now, L2 regularization is when p equals 2. We often call this L2 regularization. This does not promote the sparsity of W, as we said, and it's equivalent to the regularization used in ridge regression. So if you ever use ridge regression in linear regression literature, that's basically very similar or equivalent to the regularization used there. Again, this is just it ends up being the sum of square of the weights when p equals 2. Right, so this is the L2 regularization. The L1 regularization is equivalent to the regularization term used in lasso regression, and it tends to have, or it's more likely to give a sparse weights. Okay, there's no guarantee that you will actually get very sparse weights here, but at least it doesn't destroy sparsity, or it doesn't actively promote non-sparsity, which actually L2 regularization does. And so you're more likely to get more sparse weights here. And the L1 regularization basically amounts to just the sum of the absolute values of the weights. So here we're adding to our cost, or our loss function, the sum of square of the weights. Here we're adding the sum of the absolute values of the weights. Now, in the last couple of slides, I would like to show you another way to actually apply the regularization, which is well known in the Bayesian literature, which is that a regularization is equivalent to having some prior distribution on the weights. And the reason this is useful is, again, to help us think in terms of a higher level of abstraction, to help us think in terms of defining a prior distribution for the weights and not as a specific sort of regularization function that we can use. And this should, in theory, allow us to then define arbitrary distributions here. But often this is done just for implementation convenience, so we can easily define these regularization terms or add these regularizations in the DeepPumas and DeepPumas modeling framework, which allows us to basically put regularization on population parameters. So if we have the ability to do something called maximum a posteriori estimation in Pumas and DeepPumas, where the population parameters have a prior associated with them. And regularization essentially can be modeled using such priors, and this is the derivation for this, where if I assume that my weights W here have a normal distribution prior, with mean 0 and variance equal to like the identity matrix times sigma square. So all of the weights have the same variance. The minus log prior or minus log probability of this is going to be given by this term here, and it's going to be given by this term here, essentially, which if you look at this first term, it's actually constant. It's constant in W. Now, if I assume that sigma here has a specific value, so let's say sigma equals 1 or sigma equals 2, right? So for any specific value of sigma, this here is constant. And W is just the number of weights in W here. And so this term here is constant in W. It doesn't change with W. And this term is not constant in W. There's actually a W that shows up here, and that's actually the sum of square of all the weights, right? this here is nothing but the sum of square of all the weights, which is just square of the L2 norm of W, right? And this here is essentially our lambda. And so if I just rewrite this as lambda, and then rewrite this as the square of the L2 norm of W, and then rewrite this as some constant in W, I recover my regularization that I had before here, right? So that's the same regularization that I had before, or this term here essentially becomes lambda times this square of the L2 norm of W, and then plus some constant, right? So by minimizing a function and then a constant, the constant can be dropped because the gradient, the constant doesn't affect the minimization. The same W that minimizes this term here will be the same W that minimizes this term plus some constant, as long as this constant is a constant in W. Now this constant depends on lambda, but it's okay because lambda is just fixed up front. We just pick lambda up front and then we do the minimization or the optimization. Lambda is not really optimized directly in this case. So what I'm trying to get to here is that by defining a prior distribution that looks like this, and by controlling sigma square, I can indirectly control lambda, right? So by controlling sigma square here, it has an effect on controlling lambda. So if I double sigma square, it halves lambda, right? And if I multiply sigma square by 4, it has the effect of multiplying lambda by 1 over 4. And so I can control lambda by controlling sigma square. If I want to increase the amount of regularization, I can reduce sigma square. And if I want to decrease the amount of regularization, I can increase sigma square. So they have this negative sort of correlation or proportionality relationship, inverse proportionality relationship. So again, this is nice because that means I can treat now W as just population parameters that happen to have a prior distribution on them, just like any other population parameter in a Pumas model or a DeepPumas model. And this prior is just set to this arbitrary value where now the hyperparameter becomes not just lambda here, but actually sigma square, right? Now, for convenience, we actually allow you to also, or you can use DeepPumas and you can define lambda directly, and you can say, I want L2 regularization, and then you give it a value of lambda. But then under the hood, the way this is actually done is it converts lambda to sigma square, defines the normal distribution prior, and just uses that prior, essentially, when fitting. And so also that's why in DeepPumas, you would have to use map algorithms, not regular algorithms. If you use like FOCE or naive pooled to fit your model, normally you would have to use map of FOCE or map of naive pooled to fit your model, because without the map, the priors would actually be ignored. And so again, all regularization in DeepPumas is actually implemented under the hood using prior distributions. So the L2 regularization is going to be equivalent to the normal distribution prior. But what about the L1 regularization? Well, there is another prior distribution called the Laplace prior, or the Laplace distribution, not to be confused with the Laplace approximation or the Laplace method. Laplace is a very prolific scientist. There are many things named after him, but the Laplace distribution is different from the Laplace approximation or the Laplace method, which is perhaps more familiar in pharmacometrics. The Laplace distribution has this specific minus log PDF, this function here. And essentially it's very similar to the normal distribution, but the key difference between them is that instead of taking the square of the weights here, we actually take the absolute value of the weights, and then the normalization constant will also be different. But that's essentially what the negative of the log prior looks like. And then again, if you simplify things a bit, you get a constant here. This is constant in W, not constant in B, for example, or in NW. But NW itself is a constant. It's just the number of weights in your model. It doesn't change while you're fitting or while you're optimizing. And B here is assumed to be also a predefined constant. We can set B to 1 or 2 or 10 or whatever. And so B is also a constant when we're optimizing. The only thing that's not a constant when optimizing is actually the weights itself, because these are the main parameters that we care about optimizing. And so if we rewrite this like this, we can see that this is nothing but lambda times the L1 norm of the weights plus some constant. And so once again, we can just replace this here with some L1 norm of the weights, and then we have a constant, but the constant can be ignored when minimizing. And so by simply having this as the log likelihood, or rather the negative log likelihood, and having this as the negative log prior for some prior distribution, we can minimize this exact function here by just doing maximum a posteriori estimation. And so the idea is when you do map estimation or maximum a posteriori, you're minimizing or maximizing the log likelihood plus the log prior, or minimizing the negative log likelihood minus plus the negative log prior. And so by encoding everything using likelihoods and priors and using distributions, by using the normal distribution, for example, for the y here, and encoding our loss as just a negative log likelihood, and by using a normal distribution for the prior on w, and encoding our penalty or our regularization as the negative log prior, then by doing simple maximum a posteriori re-estimation, we are essentially minimizing this more traditional loss in deep learning. All right, so this is again the sum of square, and this is the sum of square, let's say, of the weights times some lambda or some constant lambda. And so we can achieve very similar effects or equivalent effect by just doing this more probabilistic sort of thinking, or by thinking in terms of probability distributions rather than just as simple loss functions. And again, this is much more general because for arbitrary data types here, we can define different log likelihoods or negative log likelihoods. And we also technically have the ability to define arbitrary distributions here and use them as the prior. We don't have to stick to just normal distributions and Laplace distributions. We could also get creative with these, although that's much less common, getting creative in the log prior. So this is the last slide, and there was sort of a wide variety of concepts and topics that we covered in these slides here. So we covered things like the idea of log priors and log likelihoods and cost functions. Maybe let's start from the beginning to recap. So we covered things like the architecture of a feed-forward neural network or a dense neural network, and how we go from the inputs of the hidden layers to the outputs, and what the activation function is, or what the role of the activation function is as the nonlinearity in the function that gives us the richness and the flexibility to fit and approximate nonlinear functions or nonlinear input-output relationships. And then we talked about the cost function or the training function, the loss function, that's commonly just a sum of square error or some generalization of this using the negative log likelihood. We talked about gradient descent, and we maybe missed this point here, which is that the gradient is often calculated using something called automatic differentiation, or a specific variation of automatic differentiation, which is called backpropagation. And you can see more details in this reference here. And so we've discussed briefly the idea of gradient descent and alpha, which is the step size. It's also commonly known as the learning rate in the context of deep learning, because it's helping us to learn, and it is sort of roughly or intuitively equivalent to sort of the rate or the speed by which you're learning, or the model is learning. And then we discussed that a generalization of the sum of square error would be using the negative log likelihood and defining a sum distribution for the data, and then the negative log probability of that would be essentially your loss function instead of using the sum of square error for the loss. And then we talked a bit about overfitting and underfitting, and how is it that when you train your model for long enough, you tend to overfit. We talked about the key design factors or design considerations that you need to worry about when picking a neural network and trying to apply it in a specific domain. We talked about activation functions briefly and what each activation function tends to be useful for, and then some hyperparameter search algorithms, and strategies to prevent overfitting, of which the most common we said is early stopping and regularization, at least in the DeepPumas context. That's what we tend to use the most. And then we said that always use models that are not larger than what you need, and so it's always a good idea to start from a small neural network or a small model or even a linear model, and then increase the complexity gradually until you start getting diminishing returns. Then we discussed briefly the idea of applying a penalty to the cost function as another key method to prevent overfitting. And this is commonly done in DeepPumas as well, in quite a few places. And then we said that actually this regularization types can themselves be, well, first they're equivalent to some other common methods in linear regression, like ridge regression and lasso regression, but then they can also be mapped or directly sort of related to another sort of technique or idea of using the log likelihood plus the log prior and maximizing that as our main objective, and then or minimizing their negative essentially. And then for a specific choice of a prior distribution, you actually get the same regularizing effect as just using this L2 regularization or L1 regularization. And with this, we will stop here, and there are obviously a lot more details that one can cover, and there are probably a few things that we missed, but hopefully this gives you the grounds or enough sort of background to then start applying these methods and using DeepPumas, and hopefully this makes you a bit more prepared for real life sort of applications of DeepPumas. Thanks for your attention.